In this video, we're going to start exploring the basic terminology in differential equations. So what a differential equation is, it's an equation that has an unknown function that you started out with a derivative. So we're given the derivative and we don't know what the function is, and we know that a family of functions can fit a derivative. An ordinary differential equation is the unknown function is a function of only one variable. That's what this class is all about, is ordinary differential equations, ODE. Partial difference equations, talk maybe a little bit about that in the end. And that's when the function has more than one variable. That's not this class. We're going to be mostly in ODE. We might have a little bit of partial toward the end, but not very much. The dependent variable, this is the unknown function in which the differential equation is being solved. We want to think of this as f of t or y or f of x. The independent one is usually our x. Sometimes we call it a t. Parameter is a fixed value for the problem. So like you might see mu or r or omega or h, something like that. And then the order of the derivative is the highest derivative that we see. So like our first, second, third derivative, the order would be the first derivative or the second derivative. So let's just explore these examples here where we're asked to determine the order. One is the independent, one is the dependent variable, any parameters that are in the equation. Now, when we look at the dp dt, this is our calculus notation, and we can look by our calculus notation that the variable in the denominator in dp dt, the variable in the denominator, which is t, so the derivative of p with respect to t, that we know that t would be the independent variable here, and p of t would be our dependent variable. So anything that is not p of t or t would be our parameters. So r is a parameter, k is a parameter, alpha is a parameter, beta is a parameter. And it's first order because it's the derivative of p with respect to t. It's not the second derivative of p with respect to dt2. So we know that this is a first order derivative, and you're thinking, well, what's this p shenanigans here? What is this p? Well, to make our lives a little bit easier is that we don't always write p of t everywhere. So we could write this as d of p with respect to t is equal to r of p of t multiplied by 1 minus p of t divided by k minus beta p of t, the quantity squared. And then in the denominator, I would have alpha squared plus p of t, the quantity squared. Now, totally fine to write it like that. And if it makes it easier to write it that way, absolutely. But to make our lives easier, we're just going to use a p, and it's implied p of t there. So that would be our dependent variable, which is p of t, or just p, if you will. So our first example is a first order ordinary differential equation because it is in one variable and I have a bunch of parameters. Now, my second example here, this one's a little bit easier to see that my independent is t the way that this is wrote. So this is independent is t, the dependent is x of t. Now this is different than what we normally see it, because normally what we see is we see f of x, or we might see f of t. We don't often see x of t. And it's a little confusing the first time you see it, but it just means the same thing as this function notation. The function is called x, and so our independent is t. I could have absolutely wrote this as m of x double prime plus b of x prime plus k of x and then equals 2t squared. But then it's a little bit harder to determine what is our independent and what is our dependent when it's wrote like that. Here it's much easier to determine that our independent is t, our dependent is x of t. It's a second order because the highest power on my derivative is 2, so it's an order of 2. And the parameters, again, are the values that are m, b, k, because those are not my independent or dependent. And so it is a second order differential equations, ordinary differential equations. Now, the second one that I'm looking at my third one, C, we can see that the way that this is wrote is that my dependent is y of t. Y of t is my dependent. And that's something more similar than what we normally see. We normally see it of y equals some function of x, but we can also have y equals some function of t. It's a little bit easier for us to wrap our heads around than when we see x of t, but still that is my dependent. T, of course, being my independent, and I can also tell you that based on the way that this is wrote, y of t, t being my independent, y of t being my dependent. All right, so this is still an ordinary differential equation. E is just a number, it's 2.71 each. Alpha is a parameter. Now, this one's a little harder to decipher, but this is an order 2. Now, the reason I know it's an order 2 is because I'm basically asking you to do the derivative of a derivative, right? So this notation, this is the derivative, and then they're asking you to take the derivative of a derivative. So this is a second order ordinary differential equation. My next example here is I have the partial. Now I know it's partial, so I know I am no longer in a ordinary differential equation. And I know it's partial because when I go back to calculus, we know that this is the notation for the partial derivative with respect to x of, say, our function f of xy, as an example. So that funky looking delta is the partial derivative. So we know this is a partial derivative, and it's second order because of this 2 here and also this 2 here. So I know I'm doing partial derivatives with respect to x twice of some function. And so my independents, I have 2 of them. My independents are both x and y, are both independent. My dependent is that function, my function u of x comma y, that is my dependent, and I know that this happens to be in order 2. There are no parameters because everything is my function, and it's also with respect to x and with respect to y. In particular, we have a name for this function, and by the way, this is not a ordinary differential equation because it is partial derivatives. This particular function is called the Laplace equation, L-A-P-L-A-C, Laplace's equation. So we're not going to spend much time on that, if at all. When we are looking at solutions of differential equations, it is sufficient to be able to differentiate the function, and if that is substituted into the equation, together with the necessary derivatives, we will get the equation of an identity, a true statement. This makes it true. So we want to show that the given function is a solution, and then we want to determine the largest interval or intervals, the independent variable that this solution will be defined and satisfies this equation. So if I want to think about the interval, we want to think about the values of the independent variable that will be allowed to make the original function or the differential equation undefined or defined. Depends on how you look at it. So the first thing we're going to do is we're going to take the first derivative of what this function is. So I'm going to do x prime of t. Now my independent is t, so this is going to be e raised to the negative 2t multiplied by negative 2. So in other words, it's negative 2e raised to the negative 2t. Now I have a substitution of x prime. Now I'm going to replace x prime with negative 2e raised to the negative 2t. And then I also need my second derivative. So my second derivative with t is going to be negative 2e raised to the negative 2t multiplied by another negative 2, which gives me 4e raised to the negative 2t. Now I have a replacement for x double prime. Okay, so I have 2 x double prime gets replaced with 4e raised to the negative 2t plus 6. My x prime is negative 2e raised to the negative 2t. And then plus 4, and my original function is e raised to the negative 2t. And I ask myself, does this equal 0? So I have 2 times 4, which is 8, minus 12, because that's the 6 times the negative 2, so that's the 12, and then plus 4 more. Yes, this is indeed true. So this is true. This is true. So then what is the largest value that will satisfy this? What is the interval? Well, we look at this value and we think, well, what are the restrictions on t? And there are no restrictions on t because e raised to the negative 2t is defined on all real numbers. So my interval for this, and you can either write it as set builder or interval notation. I'm good with either one. If you're going to use set builder, you would have the squiggly bracket, the t, such that t belongs to the real numbers, element of the real numbers, or you can go from negative infinity to infinity. So I'm good with either one. Now let's take a look at my next example here. So for my next example, I am asked to find just the first derivative. So here's my original function. It is a function of, with respect to t, a function of t. So I'm asked to find the first derivative. So p prime of t is going to be ce raised to the rt multiplied by r. Now, r and c are parameters. And this is why you have to take Calc 3 before you can take this classes, because we know that c and r are parameters. They're just our constants. They're just going to come along for the ride. And so I'm going to replace that with p prime. So I have CRE raised to the RT. Is this equal to r multiplied by my original function, which is CE raised to the RT? And the answer is yes, this is true. And again, we ask ourselves, what kind of restrictions can we put on t, or is there any restrictions to put on t that would make this so that is undefined? And the answer is no. So its domain is, again, I'm using t as my independent. T belongs to the real numbers, or negative infinity to infinity. All right. Now, let's take a look at my next example. So I am going to need to find x prime of t. Well, I'm going to rewrite this as t squared plus 4t plus 1 raised to the 1/2. Now I'm going to have to use the chain rule. So it is 1/2 t squared plus 4t plus 1 raised to the negative 1/2 times the derivative of the derivative of t squared plus 4t, which is 2t plus 4. Now, I can factor 2 out of this 2t plus 4, and it will cancel with this 2, which is in the denominator. When I do that, I'm going to get t squared plus 4t plus, I'm going to have, in the numerator, I'm going to have t plus 2 over the square root of t squared plus 4t plus 1. All right. Now, that's this side. So the left side is t plus 2 over the square root of t squared plus 4t plus 1. We ask ourselves, is this equal to t plus 2 over x? Well, x happens to be the square root of t squared plus 4t plus 1. So the answer is yes, this is true. So that is nothing surprising. We have to think about what the interval is. So this one's going to be a little bit more involved. To find the interval, I'm just going to erase this so I can have some space. To find the interval in which this makes it true is I have to have t squared plus 4t plus 1 to be greater than or equal to 0 because it's underneath the square root. And this doesn't factor, so I'm going to have to throw it in the quadratic. And I'm going to say that t is equal to negative 4 plus or minus the square root of 4 squared minus 4 all over 2. So t is equal to negative 4 plus or minus square root of 12, 16 minus 4 square root of 12, divided by 2, which is negative 4 plus or minus 2 the square root of 3 over 2. And so I end up with negative 2 plus or minus the square root of 3. Now, if I were to do a quick graph of this t squared plus 4t plus 1, not the entire thing, just not the square root part, just the value underneath the square root, just this t squared plus 4t plus 1. That would tell me that I would be crossing at negative 2 the square root of 3. So negative 2 the square root of 3, so negative 2 plus the square root of 3 is going to be slightly less than negative 1, or slightly less than 0. And then negative 2 minus the square root of 3 is going to be slightly less than 4. So this is what the graph would look like. So the interval that's going to make it true is the interval that goes from negative infinity to negative 2 minus the square root of 3. Union between negative 2 plus the square root of 3, comma, infinity. So this is the interval for x that would make this a true statement because that is the interval for t. That would be the interval for t that would stay in the real numbers for the original function. Let's do some more examples and give you some more definitions. The system of differential equations, that's just a set of differential equations where two or more dependent variables are related to each other by differential equations. Here's an example where I'm asked to show that the given function form a solution to the system and then determine the largest interval for the independent. So it's not much different than what we've done in the past. So the first thing I'm going to do is I'm going to say, hey, I've got an x value and I have a y value. So my x minus y, this, x minus y is going to be equal to, well, here's my x. This is e to the t cosine 2t minus 1/2 e to the t sine of 2t minus, and here's my y, e to the t cosine of 2t plus 2e to the t sine of 2t. I'm just going to simplify this, and when I simplify this, you can see my e to the t and my negative e to the t is going to cancel out. So this one and this one will cancel out. This will end up becoming, I have negative 1/2 and then I have minus 2 more. So that gives me negative 5 over 2 e to the t, the sine of 2t. So now I'm just going to see whether or not when I take the derivative of x, I'm going to go back here and I'm going to say, okay, let's take this derivative of x. Do I end up with this as the answer? So I'm going to take x prime. Now when I do x prime, remember that I'm going to have to do, I am going to have to do the product rule. So the derivative of e to the t is e to the t cosine of 2t. And then I have to do the derivative of cosine. So that's going to be negative sine of 2t, e to the 2t, multiplied by the derivative of the angle, which is 2. That's the first part. And then minus, and then I'm going to go ahead and take the derivative of 1/2 e to the t sine of 2t. So this is going to be minus 1/2 e to the t sine of 2t, and then I'm going to take the derivative of the sine of 2t, so this is going to be plus 1/2 multiplied by 2, the cosine of 2t, and then e to the t. So that's the derivative of x, and now I just got to make sure that this all works out. And you can see that this e to the cosine 2t, these two cancel, and the negative goes through, will cancel with this. So this and this will cancel. And then I end up with 2 sine 2t e to the 2t minus 1/2 e to the t sine of 2t, which gives me exactly what I had when I did that subtraction of x and y. So you can see that, yes, this does indeed work out. Now, I would also have to do the same thing with this one, as I'd go through and make sure the same thing works for y prime, that it's going to be equal to 4 times the x value plus y. And I would do the same thing down here for b. And I'll let you all work on those. And that's it. Nice, easy introduction to differential equations.